Welcome to Chapter 16. In Chapter 16, we're going to take our knowledge of equilibrium chemistry and we're going to apply it to acids and bases. So in this chapter, we're going to look at the definitions of acids and bases. We're going to look at applying those definitions with equilibrium chemistry to understand things like pH, hydronium ion concentration, and behaviors of acids and bases. So, acids and bases are very common chemicals, categories of chemicals. We've known about acids and bases since ancient times. If we were an old-fashioned chemist, you might taste your chemicals to figure out what they are. I don't suggest it nowadays. But anything you find that tastes sour, okay, has an acid in it. So if we think about foods like citrus fruits, vinegar, think about a lemon or Sour Patch Kids. Anything like that has an acid in it, and that sour taste is coming from the acids. Acids also have the ability to dissolve metals. They react with the metals and form compounds, and the acid gets eaten away. Bases are often found in are not often found in foods. Okay, they're not usually safe to consume. But if you were to taste a base, okay, they're going to be bitter. So they talk about potassium cyanide tasting like bitter metal almonds. It's an old-fashioned way to poison somebody. Okay? If you think about bases, they're found mainly in cleaners, oven cleaners, Windex, ammonia, heavy-duty bases. If we consume it in a salt, basic ions are found in Tums and Rolates. That's how an antacid works. And bases in solution feel slippery to the touch. Now, a reaction between an acid and base is called a neutralization reaction. It's called a neutralization reaction because they neutralize each other's properties. They cancel out each other's properties. It's not because they create a neutral solution. They could create a quote-unquote neutral solution, but that's not always the case. Now, there are three different definitions for acids and bases. We're going to start with the simplest definition of acids and bases, and then we're going to work our way to the more complicated definitions. So our first definition is Arrhenius's definition. Now, we've met Arrhenius before. He was involved with working out activation energy and kind of starting us down the road of reaction mechanisms. He's responsible for the collision theory, okay? When we were back in chapter 14, I know I'm bringing up nightmares. So we're going to go with his definition of acids and bases. According to Arrhenius, an acid is a compound that contains hydrogen and when dissolved in water ionizes, okay? It actually reacts with the water to form hydronium ions. So let's look at the process of an acid like HCl dissolving up in water. Okay? So HCl gas dissolves up in water to give us HCl aqueous. Now, the HCl aqueous does not just sit there and float in the water. It reacts with water to produce hydronium ions and chloride ions. Okay? So this is the definition of an acid. The acid molecule reacts with water to give us hydronium ions and an anion. Okay? Remember, we're going to recognize an acid when we see its formula written because hydrogen is going to be written first. A base is a salt that contains the hydroxide ion. Okay? When a base dissolves up in water, the process of dissolving the base up in water is a dissociation. It's an ionic compound. the ions just separate. So sodium hydroxide solid in the presence of water gives us sodium ions and hydroxide ions. So acids ionize in water. We create ions where there were none to begin with. Bases dissociate in water. The ions that are there just separate from each other. So a reaction between an acid and a base, if we're looking at it on the molecular level, what's really going on is I have a hydronium ion, a chloride ion, a sodium ion, and a hydroxide ion going to water molecules plus sodium ions and chloride ions. Okay, now notice the sodium ions, chloride ions cancel out because they're on opposite sides of the reaction arrow. Okay? And if I remove them as spectator ions, what we see is hydronium ion plus hydroxide ion going to water. Sometimes this reaction is written as H plus OH minus going to 1 water. This is more realistic, but this we see a lot. Okay? So, the reaction between an acid and a base. Now, Arrhenius with his definition understood very quickly that not all acids are created equal. Some acids are better at reacting with water, undergoing that ionization reaction, than others. Acids that 100% ionize in water are called strong acids. The reaction with water here has a very, 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 very large equilibrium constant, and we would refer to them in this process as going to completion. Okay? So every HCl molecule I put into water solution reacts with water to give me hydronium ions and chloride ions. So all we have in the end is a solution of hydronium ions, chloride ions in water. Then we have weak acids. Weak acids do not 100% ionize in water. Okay? So these acids, when they react with water, give us a equilibrium such that we have a measurable equilibrium constant, and we have measurable amounts of the intact acid, the hydronium ion, and the ion in solution. Okay? Now, the really weird thing here, or the interesting thing, is that, you either go about 100% ionization or 10% or less ionization. There is not a big continuum of ionization percentages for acids. You're either really, 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 really good at giving up, reacting with water, or you're going, not very good. Okay? So for acids, it sometimes seems like it's almost all or nothing. So why Arrhenius was looking at strong acids was because he had been looking at the enthalpy of reaction between strong acid and a strong base. And every time he did the reaction between any strong acid and any strong base, he kept getting the same delta H of reaction. Now here, let me show you kind of what I'm talking about. Okay? Now let's look at overall reactions. I'm going to show you two. So if I had HNO3 aqueous plus NaOH aqueous going to H2O liquid plus NaNO3 aqueous. Okay? And we got the delta H here. I'm just going to call it X. Okay? Well, no, I'll create a value. Let's call it 300 kilojoules. And then he looked at HCl aqueous plus KOH aqueous, and he got water liquid, and he got potassium chloride aqueous. and he got a delta H here, and these are negative because it's exothermic, 300 kilojoules. He kept getting the same delta H, and he asked the question why. Okay? Now, if I break down what's going on here, HCl aqueous is hydronium ions plus chloride ions. Aqueous, aqueous. And potassium hydroxide is potassium ions, aqueous, and hydroxide ions, aqueous. And then I got water and potassium chloride aqueous. Well, I'm going to cheat a little bit here. Let's just make this H plus aqueous. H plus really can't exist in water. Okay, now notice potassium ion appear on both sides, are going to cancel out. Chloride ion and chloride ion appear on both sides, it cancels out. So we get H plus plus OH minus going to H2O liquid. Actually, this goes 100%. If I do the same thing with the nitric acid, I'd have H plus aqueous plus nitrate ions aqueous plus sodium ions aqueous plus hydroxide ions aqueous going to water liquid plus sodium aqueous and nitrate aqueous. And again, notice that sodium ions and sodium ions are on both sides, they cancel out. The nitrate ion and the nitrate ion are on both sides, they cancel out. So we get H plus plus OH minus going to water. Sorry about the mess, guys, but I'm stretching. So what Arrhenius figured out was that anytime he reacted a strong acid and a strong base, really the underlying net ionic equation was the same. And that explained why he kept getting the same delta H for the reaction. Okay? So his underlying reaction was actually hydronium ions plus hydroxide ions going to water. What was confusing people was the presence of those spectator ions. Okay? So beautiful, elegant solution to a conundrum. Now, let's move on to weak acids. Weak acids have varying strengths. Now, what do we mean by a strength of an acid? The strength of an acid is a statement about the concentration of hydronium ions at equilibrium compared to the concentration of the acid initially. For a strong acid, the concentration of hydronium ions at equilibrium, or at completion, is equal to the concentration of the strong acid you began with. Okay? For a weak acid, the concentration of hydronium ion at equilibrium is less than the initial concentration of the acid. For most weak acids, the hydronium ion is going to be 5% or less the original concentration of the hydronium ion. So, when we talk about strong acids and weak acids, but we also use the terms stronger and weaker. When we use the term stronger and weaker, what we're doing is a head-to-head comparison of the percentage of hydronium ions produced relative to the amount of acid you started out with. weaker acids produce fewer hydronium ions in solution for the same initial concentration than a stronger acid. Both acids could be weak acids, but we're just doing a head-to-head comparison. Okay? So if I were to compare hypochlorous acid versus nitrous acid, and I had the same concentration of acid initially in solution, and I looked at their concentration of hydronium ions after the system has come to equilibrium, the one that had the higher hydronium ion concentrations would be the stronger acid out of the group. Okay? Now, when we're dealing with acids and their behavior in water, we can have a generic reaction. HA aqueous plus water liquid goes to hydronium ions aqueous and an anion. Okay? And we use the double arrow because being a weak acid, this system comes to equilibrium. It does not go to completion, 100% conversion of HA to hydronium ion and A-. So we can write a generic equilibrium expression. The K is going to equal hydronium ion concentration over anion concentration over HA, weak acid concentration. Okay? Water is not included in this equilibrium expression because water is a pure substance. Notice its subscript is L for liquid. Now, because this is an equilibrium expression for an acid ionization, it gets the symbol Ka, little subscript A. The A says that this is an acid ionization constant. Fancy way of saying that you got an equilibrium constant for the acid ionization reaction. Okay? So let's look at a few acids and let's write their reactions and then write their Ka expressions. All right, over we go. So let's give ourselves some working room here. Now, guys, given an acid, you're supposed to be able to write this reaction with water. It doesn't have to be given to you. So if I've got the acid HClO, hypochlorous acid, aqueous, I bring it in contact with water liquid, double arrows, I'm going to get some hydronium ions aqueous and some hypochlorite ions aqueous. Okay? The Ka for this is just going to be hydronium ion, hypochlorite ion over hypochlorous acid concentration. Okay? If we had the acid HF, hydrofluoric acid, you may want to go back and remember how you name things. Water, liquid, goes to H3O plus aqueous plus fluoride ions aqueous. And the Ka here, hydronium ion, fluoride ion, HF. Okay, so notice it's following that generic pattern. HA aqueous plus water liquid going to H3O plus, A minus, aqueous, aqueous. Ka is always equal to hydronium ion concentration, A minus concentration, all over HA. Guys, this means if you don't know what the formula of an acid is when you're given its name, you can always work it using the generic. Okay? Now, Kas are a window into the strength of an acid, the percentage of an acid's percentage of acid molecules that are going to be converted to hydronium ion. Okay? The stronger the weak acid, the larger its Ka is going to be. So let me show you a table where we can do some kind of comparisons. 695 in your textbook. Okay, let me flip over to the document cam. All right. Okay, guys, here is table 16.5 on page 695 in your textbook. Okay, let me pull this up a little bit. Now, here are some weak acids, okay, and their Ka values. So, chlorous acid has a Ka value of 1.2 times 10 to the minus 2. Nitrous acid has a Ka value of 4.6 times 10 to the minus 4. Hydrofluoric acid, 1.6 times 10 to the minus 4. Formic acid, 1.8 times 10 to the minus 4. If I were to look at just the acids that are showing here, of these 6 acids, the strongest acid in the group is hypochlorous acid because it has the largest Ka. The weakest in this group is acetic acid, and the strength of the acid decreases as we're going down the length here. So if I had a 1 molar solution of hypochlorous acid and a 1 molar solution of acetic acid, the concentration of hydronium ions in the hypochlorous acid solution is going to be larger than the concentration of hydronium ions in the acetic acid 1 molar solution. Okay? Now, let's switch back to our notes. Okay? So here's some general things to remember. Here's a list of strong acids. HCl, HBr, and HI, the hydrogen halides below fluorine, are all strong acids. Oxoacids with 2 or more oxygens than the number of hydrogens are strong acids. So HClO4, H2SO4, HClO3 are strong acids. Okay, our list of strong acids, not very big. Okay, then we have our weak acids. HF is a weak acid. All acids where the hydrogen are not bonded to an oxygen or a halogen are weak acids. So H2S is a weak acid. Oxoacids where the number of oxygen is not 2 or more the number of hydrogens. So HClO, HNO2, H2SO3 are all weak acids. Carboxylic acids are weak acids. In the formula, you're going to see a COOH or a CO2H. Okay, so let me show you a few of these just so that you kind of have some references. Okay, so if we had acetic acid, CH3COOH. Okay, you could also see it written CH3CO2H. Structurally, doing its Lewis dot structure, looks like this. The acidic hydrogen is this guy. That's the donatable hydrogen. The hydrogen here is experiencing electron density pull from the oxygen. It's in a very lopsided bond, and because of this double bond oxygen over here to the carbon, electron density keeps being pulled away from that hydrogen. So this is a removable hydrogen, not those 3. Okay, so anytime we have this is a carboxylic acid. So any of the organic acids are carboxylic acids. and they're going to have that kind of group, COOH. Okay, so things like HClO, HClO2, H2SO3, HNO2, carboxylic acids, HF. These are all examples of weak acids. Okay? HCl, HBr, HNO3, HClO3, HClO4, H2SO4 are all examples of, HI, all examples of strong acids. Another example of a weak acid is H2S. So these are strong. These are weak. Examples of weak and strong acids. Okay? Now, according to Arrhenius, a base is a hydroxide ion containing salt. So a strong base under the Arrhenius definition has to contain the hydroxide ion and has to dissolve up well in water. So remember that we're dealing with a salt. So to have a salt that dissolves up well in water, you have to have one of the weaker ionic bonds. So strong Arrhenius bases are salts of the alkali metals and the lower members of the alkaline earth metals, calcium, strontium, and barium. So there's actually a very limited number of strong bases under the Arrhenius definition. Okay? So if we look at our strong base list, it's going to be LiOH, NaOH, it's going to be lithium, sodium, potassium hydroxide. Those are the ones most common. Of course, there are other members of the alkaline metal family. There's rubidium, cesium, and francium, but we're really not going to encounter those too often. Calcium hydroxide, barium hydroxide, and strontium hydroxide are also considered strong bases, although they don't dissolve up like the lithium, sodium, and potassium hydroxide do. Okay? Now, when we get into other definitions of acids and bases, we're going to expand out our definition of bases, and we'll encounter some new strong bases there. Okay? All right. Arrhenius figured out fairly early on that there was a problem with his definition of acids and bases. And what gave him an inkling that he had a problem with acids and base definition was ammonia.